right, we're doing a fast version of number 20, which is the one with the coefficient of friction. So read it. Shem, you're in charge of reading.
Okay. A 16-kilogram sled is being pulled along the horizontal snow-covered ground by a horizontal force of 24 newtons. Starting from rest, the sled attains a speed of 2 meters per second and 8.0 meters. Find the coefficient of kinetic friction between the runners of the sled and the snow.
All right, so I just quickly wrote down all the stuff that Shem said as she was writing it, as she was reading it. All right, so the mass of the sled is 16 kilograms, force is 24 newtons. It's being applied parallel to the displacement, right? It's a horizontal force, it said. All right, so if it's that way, that means that these guys must be that way too if it starts off at zeros and gets to 2 meters per second. Okay? Everybody got what we're saying? All right, so the basic relationship we're looking at here, this is from section 6.2, sometimes that's a clue, is the work-energy relationship, right? Work-energy theorem says that what? Anybody? There it is. Thank you, Jason. Work is equal to change in kinetic energy. Okay? So, what is the work done? What is the change in kinetic energy? All right, so we have to consider both the force, what forces, not just the applied force, but since we're being asked what the coefficient of friction is, I guess we have to assume also what? That friction is present. That's all I'm looking for. All right, so free body diagram. What do we have here? We have normal force, we've got weight, we've got the applied force, and we've got friction. Notice which one's bigger. The applied force has to be bigger. How do we know that? It's accelerating, right. There's a net force acting this way. Okay? Everybody okay with that? All right. I hope. So now we know that the total amount of work, net work, is equal to the change in kinetic energy. I already wrote that, but I'm rewriting it. So how are we going to do net work? We could do one of two ways. We could say the work done by the net force, or we could say the work done by the individual forces. For me, in this case, seems to be easier to first find the net force. Okay? Rather than finding the work done by each force, which requires calculations, for each one, we just find the net force, and then we find the work done by the net force. All right? So we're going to say that's the work done by the net force is going to be equal to the change in kinetic energy. All right? So, change in kinetic energy, let's go back and look at that. Change in kinetic energy, we can just say it's going to be K final minus K initial, right? Right? And what's our initial kinetic energy? 0, right, because why? Yeah, because we start from rest, right. Its initial velocity is 0, so it has 0 kinetic energy. So the work done by the net force is going to be equal to the net force times the distance, the displacement, times the cosine of the angle. But what angle are we talking about? Are you sure? Let's just tell me in general, the angle between the net force and the displacement. Okay, we've got to remember always what we're measuring our angle relative to. All right, and that's going to be equal to kinetic energy at the end is going to be what? What's our 1/2 mv final squared. Okay, that's our final kinetic energy. All right, net force is going to be equal to the sum of our two forces. Well, we have this is in the positive direction, this is in the negative direction. So all we got to do is say F minus kinetic friction times the distance times the cosine of the angle between the net force and the displacement is equal to 1/2 mv squared. Notice I haven't done the cosine yet because I don't know what direction our net force is going to be. All right, so we have a force is, what was it, 24 newtons? All right, so we have 24 newtons minus frictional force. We don't know what frictional force is yet. That's not what we're trying to find, isn't it? All right, but what can we break frictional force down into? Mu kinetic times normal force. Can we just say it's mg? Well, we know that these are balanced. We're constrained to move in the horizontal, right? So we're on a horizontal surface. There's no vertical acceleration. So that means that the normal force is equal to mg. So we're going to say mu k times mg all of this in parentheses times d cosine theta is equal to 1/2 mv squared. Well, let me ask you a question. If we're accelerating in this direction, don't we know that the net force is greater, or that the net force must be pointed in that direction? Yeah? So if the net force is in that direction, and displacement is in that direction, the angle between them is what? 0, all right? And so cosine of theta is going to be equal to 1. So we can just drop that cosine term, all right? So let's go down here and we'll drop that cosine term, all right? And so now, since we're solving for mu here, we're going to have to distribute that d and do some rearranging, okay? So we got, I'm just going to go back to calling this f, okay, until I'm done rearranging. All right, so we're going to say FD cosine, whoops, we already got rid of that. We're going to say FD minus mu K mgd, distributing, is equal to 1/2 mv squared. All right, so now we're going to add this to each side and subtract this from each side, right, to get them over opposite sides. So we're going to say FD minus 1/2 mv squared, adding that is equal to mu k times mgd. Trying to isolate mu, I'm just going to flip them over again like this, okay? So we're going to say mu k is equal to fd minus 1/2 mv squared over mgd. Okay? So now if we were going to be really weird, we could, get rid of this 1/2 here, but let's just go ahead and calculate all that stuff. All right? So mu k is going to be equal to, the force was 24 newtons, distance was 8 meters. Is that correct?
Yes.
All right, so 8 meters minus 1/2 m. M was 16. All right, so let's just shortcut that and just say 8 kilograms, because that's 1/2 of 16. And so 2 meters per second, that whole thing squared, over 16 kilograms times 9.8 meters per second squared times 8 meters. All right, there's a lot of math in there, but it's all calculator math. But real quickly, let's take a look dimensionally. We've got newtons times meters here. Okay, let me just do that in green. Newton meters, and then we've got kilogram meters squared per second squared. That's also Newton meters or joules, right? Joules divided by kilogram meters squared, kilogram meters squared per second squared, joules. So we got joules divided by joules. That's just that's dimensionless, right? That's what we're looking for with the coefficient of friction anyway. So when we put all that junk in, we get something like 0.127 something, 128. Anyone? 128, okay? So that's how we did that. Now I know I did that fast, but that's for the purposes of